What is a reverse biasing and how a diode is reverse biased? Let's see this first. When the P region of the diode is connected with the negative terminal of the battery and N region of the diode is connected with the positive terminal of the battery. Just you see, the P region is connected with the negative or the N region is connected with the positive, or in the simple word you can say, when the P region of the diode is at the low potential and N region of the diode is at the high potential, then we say the diode is reverse biased. That is called reverse biasing of the diode. What is special about this type of the biasing? In this type of the biasing, either no current passes through the diode or extremely small current which is voltage independent passes through the diode, and that current is due to the minority current carriers. Just to see who are the minority current carriers in the N side, holes, and who are the minority current carriers in the P side, they are the electrons. Whereas in forward biasing of the diode, the current is due to the majority current carriers, and there a large amount current, but in the order of milliampere passes in comparison to the current in reverse biasing, which is in the order of microampere. The current in forward biasing passes in the order of milliampere. Now what happens, let's see in the detail. In the reverse biasing, why there is no current in the reverse biasing and why there is a extremely small current due to the minority, and why it is voltage independent. All these things let's see. So let's start here. When we give a potential difference or we reverse the direction of the potential difference, then what happens? This terminal receives the positive polarity and this terminal receives the negative polarity. As a result, this potential difference falls from this direction to this direction, because this external electric field is applied in this direction, so there is a potential drop across this. But the most of the potential drop of this value take place only across the depletion layer, because I told in the depletion layer there is net charge 0, and this depletion layer has a high value of the resistance. Why it has a high value of resistance? Because this is the depletion layer only which had stopped any type of the diffusion of the current carriers. So this depletion layer has a high value of resistance. So most of the part of this potential drops across this depletion layer. Now when we apply this reverse voltage, we should call it reverse voltage. So what happens? The effective voltage across the depletion layer become VB plus V. VB is the value of barrier potential, and that potential difference across the depletion layer VB in the same direction. And your applied voltage V also goes in the same direction. Drop is in the same direction. So here the effective potential drop across the depletion layer increases. What does it mean? It means that the width of your depletion layer now increased. The width of the depletion layer has been increased from this one to this much. Due to increase in the width of the depletion layer, the diffusion of majority current carriers stops completely, and that's why no current passes through the diode. But these minority current carriers are supported with this reversed voltage, and so they somehow become able to cross the junction. Means minority current carrier hole from the N region crosses the junction and moves into the P region. And the electron is the minority current carrier in the P region, crosses the junction and reaches the N region. Thus, a very small amount of the current is developed because of the diffusion or because of the movement of these minority current carriers. And since there are very few in the number, that's why the energy of these minority current carriers is sufficient because of this voltage to cross this junction. So almost this crossing of the minority current carriers become independent of the supplied voltage. Since these minority current carriers are able to cross the junction even at any voltage, therefore the current due to this minority current carrier, which is in the order of microampere, is almost independent of this. But what happens if we keep on increasing the reverse voltage? So the energy of the current carriers in the N region and the energy of current carriers in the P region keeps on increasing. And there comes a time when a large number of covalent bonds in the N region and in the P region are broken because of that increased value of the reverse voltage. That reverse voltage where the covalents are broken and large number of electron hole pairs are generated in both the region. This particular reverse voltage is known as breakdown voltage. And at this breakdown voltage, in this N region, a large number of electron hole pairs, and the same thing happens with the P region also, that is a large number of current carriers are produced. And since here the holes are minority, but after the breakdown, the number of holes, that is number of minority current carriers, increases suddenly. And the same thing happens here also. Due to the breakdown, here the electrons are in the minority, but after the breakdown we get much more number of electrons, that is the minority current carriers increases in this region also. And due to increase in the minority current carriers, the current increases suddenly at the breakdown voltage. That breakdown voltage where the current increases suddenly in reverse biasing is known as Jenner breakdown voltage. And that breakdown is known as Jenner breakdown. So now let's see, if there is a small current, although due to the minority current carriers only, so how this value of minority current carrier current, that is the current due to minority current carriers, depends on the voltage. As discussed initially before the breakdown, this current is extremely small and almost independent of the voltage. So if we represent this all the things in the graph, so the variation in the current with the voltage is known as the characteristic. So now I am discussing the reverse bias characteristic. Characteristic of diode in reverse biased. So voltage is reversed, so I have represented the voltage along the negative x-axis, and the direction of current, just you see, is also reversed. In the forward biasing, just you see, this is the polarity and this is the direction of current. Now the direction of voltage and hence the direction of current, if any, that is reversed. So I am plotting the graph in the third quadrant. Now if we want to study this characteristic with the help of this circuit, so we need to connect a voltmeter and a meter. So certainly we will follow the same rules for the connection of the voltmeter and the ammeter. How the voltmeter is connected? Voltmeter is connected parallel. So I want to measure the voltage across the diode. So across the diode in the parallel, I will connect the voltmeter. Positive terminal of the voltmeter with the positive terminal of the battery, negative terminal with the negative terminal of the battery. So any change in the voltage if I will make, so this voltmeter will read that change, and any change in the current if will be there, so for that measuring that current we need to connect the ammeter. Ammeters are connected in series. So here in the series, maybe here or maybe here, anywhere I will connect one ammeter in series. This is the negative terminal, so this will be the negative terminal of the ammeter and this is the positive terminal of the ammeter. But the current is very small, so here I will connect the microammeter. And the same type of the connection we will do in the forward bias as well, but here the ammeter will be a milliammeter. And for measuring the voltage, of course we will connect a voltmeter parallel to the diode. So for recording any change in the voltage and any change in the current, we need to connect the voltmeter and the ammeter. And now, as discussed, initially there is no current. In the reverse biasing, the width of depletion layer increases. Effective value of the potential drop across the depletion layer, that is barrier potential, increases. So no majority current carrier can cross the junction, only the minority current carriers can cross the junction even at a small voltage. And if we increase the voltage, so the current will not be affected, means the value of current is almost very small and independent of the voltage. Just you see, I am increasing the voltage but the value of current is almost constant. Now just you see. But I told there happens to be a voltage that is called reverse breakdown voltage or Zener breakdown voltage, where large number of current carriers are obtained in both the side of the diode, in the P side, in the N side. So suddenly the number of minority current carriers in the both region increases. As a result, the current increases suddenly. And that negative reverse voltage is known as Zener breakdown voltage, VZ. So this is the breakdown voltage. Now let's see what happens about the resistance. The very simple observation, just you see, before the breakdown, there is almost a very small current. So it's very easy to understand, if through any device, if a very small current is passing even at a high voltage, then that is the only one meaning, that it has a high resistance. You can understand it with the width of the depletion layer as well. As I told, the most of the resistance is there across the depletion layer only. And here the width of the depletion layer increases. It means the resistance in the reverse biased increases. In the reverse bias, there is a high resistance in comparison to that of the forward bias. Yes, after breakdown, since the current increases rapidly, so after breakdown, the resistance decreases rapidly. But before the breakdown, resistance is very high. So again, this type of the biasing of the diode does not follow the Ohm's law. I had already told the diodes are non-ohmic conductors, non-ohmic materials. So they do not follow Ohm's law. Graph is not straight. Again, how to find this resistance? Resistance is also not straight. Resistance is also not constant. So how to find the resistance? So there will be a dynamic resistance. I will represent with small r, and again that is delta V by delta I. That is. So this is what we say, a dynamic resistance, which is very high, and the most part of the resistance is there in the depletion layer only. How to represent the barrier potential? Just you see, this is the junction, and this is the P region, this is the N region, and this is the initial width of the depletion layer. This is the initial width of the depletion layer. This is the junction. This side of the junction, there is accumulation of positive charge. And this side of the junction, in the side of P-type semiconductor, there is accumulation of negative charge. So net charge in the depletion layer is 0. There is no current carrier in this region. So the resistance is very high. Now, in the reverse biasing, what happened? In the reverse biasing, your width of the depletion layer has increased. Now, this is the width. So, if the width of depletion layer has been increased, it means the resistance has been increased. There are more positive charges in this side and more negative charges in this side. So from the normal value, what was going, if I plot a graph, so this is the junction line. This is I am considering as x-axis, and this one I am considering as y-axis. So here there is a negative potential, and here there is a positive potential. This is for the unbiased, when there is no biasing. So this was the depletion layer, and this is the positive potential, this is the negative potential. So in case of unbiasing, this is the barrier potential, or barrier height we call it as well. But what happens after the reverse biasing? After the reverse biasing, just you see, after the reverse biasing, width of depletion layer increases. So there are more positive immobile charges. So the positive potential also increases, just you see. And more negative charges, so negative potential also here, just you see, increases. Now what is this? Is the new graph after the reverse biasing. Now just you see, this is the potential difference from positive to negative. That is, barrier potential has been increased in the reverse biasing, and in forward biasing, the barrier potential decreases. So this is how a diode is reverse biased And what are the special things in the reverse bias? There is no current in the reverse bias. Due to the majority current carriers, only a minority current carriers can cause a very small amount of the current. Width of depletion layer increases. The dynamic resistance has a very high value. So these are few things that we should be remembering about the reverse biasing of the diode. And remember, the characteristic of diode is a very important for everyone to understand. And whenever we say about the characteristic, so it means that we are talking about the variation in current with the voltage. So plot the graph to show the variation. Just you see, I have plotted the graph in the reverse biasing. Plot a graph in the forward biasing and just you explain the graph. What you are obtaining, what are the key features that you are obtaining from the graph. Just you note down, that is the characteristic. Now after studying the characteristic, now we will start the study of usage of diode. So in the next video, we will study a diode as a rectifier. After studying the working of PN junction diode and the characteristics of PN junction diode in forward bias and when the diode is reverse biased, let's try to solve one question. Suppose that this is the characteristic curve of a PN junction diode. Obviously this is in the forward biased and this is in the reverse biased. One on the y-axis, the current in the forward biasing I am representing in milliampere, whereas the current in the reverse biasing I am representing in microampere. So this quadrant is representing the characteristic curve in forward bias, and this quadrant is representing the characteristic of PN junction diode in reverse biased. So microampere is the current. On the x-axis I am representing voltage. This is the forward voltage, 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, and this is the reverse voltage, 5 volt, 10 volt, 15 volt and 20 volt. As we had discussed that current in the reverse biasing is due to the minority current carriers and they are voltage independent. Just you see that here is shown in the curve that the current is almost independent and has a very small value in the order of microampere. Now the question is asked here, what is the resistance offered by the diode when the current is 40 milliampere? When the current is 40 milliampere, so what is the resistance offered by the diode? This is the question. We know that in the diode or in the semiconductor devices, the resistance is not constant because they do not follow Ohm's law. So we study the dynamic resistance. So how we will calculate? The formula is there, dynamic resistance, delta V upon delta I. So just I am imagining that when the current is 40 milliampere, so there is a part of this graph, this much part, which starts from 30 to 50 at equal range from the both side from the 40 milliampere. So this part of the graph I am imagining is a straight. Remember, I have taken the equal space in the both side of the 40 milliampere point, 50 and 30. So now I am going to calculate the graph for this much portion. Now I am going to calculate the resistance for this much part of the graph. So for the 30 milliampere current, the voltage is 3 volt, and for the 50 milliampere current the voltage is 4 volt. For the 30 milliampere current the voltage, corresponding voltage is 3 volt, and for the 50 milliampere current the corresponding voltage is 4 volt. So thus this will be a triangle where this will be the value of delta V and this will be the value of delta I. So the dynamic resistance, the value in forward biasing will be delta V by delta I, and the value of delta V is 4 minus 3, that is 4 minus 3 volt, and this value, the current, delta I for 50 milliampere minus 30 milliampere, so 50 minus 30, and they are in the milliampere, so we should convert into in the ampere. Now when calculating we get 1 upon 20 and 10 to the power minus 3 is there, 10 to the power 3. So this is 1000 divided by 20. So on solving this we will get 50 ohm. That is dynamic resistance when the current is 40 milliampere is on average this is 50 ohm. Now similarly, if I ask what is the resistance offered by the diode when the voltage is minus 10 volt, remember if I have used the minus sign, so I am talking about this voltage. Minus is the reverse voltage, means in the reverse biasing. So again in the reverse biasing, now I will find the dynamic resistance delta V by delta I. But here the current is almost independent of the voltage, so current is constant, almost independent of the voltage. So simply we can write V by I. And the voltage is 10 volt, so the value of voltage is 10 volt, and the corresponding value of current at the 10 volt is 10 microampere. So this 10 micro means 10 to the power minus 6. V by I 10 volt, and the current corresponding to 10 volt is 10 microampere. So V by I this is. So the resistance offered by the diode when the voltage is minus 10 volt is 10 to the power 6 ohm. Now you can find the resistance in forward biasing is coming to be 50 ohm, where the resistance in the reverse biasing is coming to 10 to the power 6 ohm. So that we had discussed when we were studying the characteristic, that in reverse biasing the resistance is high and in forward biasing resistance is very low. So this is how, using the characteristic curve, we can calculate the resistance offered by the diode. Now let's see one more question of the semiconductor. So here it is. Suppose a pure silicon crystal has 5 into 10 to the power 28 atoms per meter cube. So this is the density, atomic density of the crystal, that in 1 meter cube this much atoms are supposed to be in the silicon. And this silicon is doped by 1 ppm concentration of pentavalent. Just to remember, when a pure semiconductor is doped, then we obtain extrinsic semiconductor. And when a pure semiconductor is doped by pentavalent impurity, then we obtain which type of the extrinsic semiconductor? N type of extrinsic semiconductor. And we have studied in the N type of semiconductor, the number density of electrons is more than the number density of holes. So let's verify that with this example. So this is the atomic density of the silicon and it is doped by 1 ppm of pentavalent. Now we have to calculate the number of electrons and the holes. We know that at equilibrium, the total current carriers, means if I am talking about the total current carriers, so I am talking about the electrons and the holes. So the number density of current carriers, that is represented by Ni. This is the number density of current carriers, means number of current carriers per unit volume, is related with the number density of electrons and the number density of holes according to this equation. Almost generally this is. When we will study in the higher classes, we will study the electronics, then we will find some more modified form. So this is the general equation which relates the relation between the density, number density of current carriers with the number density of electrons and the holes. Here the number density of current carriers is given 1.5 into 10 to the power 16 per meter cube. And just to recall, when we were studying the extrinsic semiconductor, then we had studied in the N type of semiconductor, when pentavalent impurity is added, so this pentavalent impurity provide 1 electron by 1 atom. So now let's calculate, if the concentration is 1 ppm of pentavalent, so how many atoms are there in this crystal, silicon crystal? Let us calculate how many atoms of pentavalent, that is phosphorus, is present in 1 meter cube of the crystal. You can say with the unitary method we can calculate. So 1 ppm, 1 part per million is there. So in 1 meter cube, there is 5 into 10 to the power 28 atoms. And how many dopants you have? And there is 1 phosphorus, 1 pentavalent impurity in 10 to the power 6 atoms, means 1 ppm, 1 part per million. So in 1 million there is 10 to the power 6 atom. So out of 10 to the power 6 atom, there is only 1 atom of phosphorus is there. So how many phosphorus atoms will be there in this much atom? Therefore, total number of pentavalent, that is phosphorus atom in the crystal, So if 10 to the power 6 atom, out of this much atom, there is only 1 atom of phosphorus. So these much atoms are present in the crystal. So out of these much atoms, how many phosphorus atoms will be there, pentavalent atoms will be there? So that can be calculated, 5 into 10 to the power 28 atoms. And 1 atom is there out of 10 to the power 6. So 1 atom out of 10 to the power 6 will be written 1 out of 10 to the power 6. 1 atom out of 10 to the power 6. So the final answer will be 5 into 10 to the power 22 atoms. of pentavalent impurity. We know that one atom provide one electron. So there are total this much atoms in 1 meter cube. So number of electrons in 1 meter cube, because the crystal volume was 1 meter cube. So in 1 meter cube there will be how many electrons? 5 into 10 to the power 22 electrons. And in 1 meter cube the number of electrons is known as number density of electrons, that you have got 5 into 10 to the power 22. This is. Let's calculate the number of holes as well. So we have the relation between number density of electrons, number density of holes, and the number density of current carriers. This is. So using this equation, if we try to find the number density of holes, that number of holes in unit volume, so number density of holes will be equals to number density of current carriers square upon number density of electrons. The number density of current carriers is given 1.5 into 10 to the power 16. So if we make the square, so it will be 2.25 into 10 to the power 32 square divided by, we have got the number density of electrons, we have calculated 5 into 10 to the power 22. Now if we solve, then we will find the number density of holes is, this is 0.45 into 10 to the power 10, or we can say 4.5 into 10 to the power 9, number density of holes. Now just to compare number density of electrons and number density of holes. The number density of electrons is much larger than the number density of holes. And this we had studied when we were studying N-type semiconductor. That when a pure semiconductor is doped with pentavalent, then we obtain N-type semiconductor, and in the N-type semiconductor the number density of electrons is greater than number density of holes, and this is verified by this example. So here I have used this equation, a general equation. With the unitary method we have calculated the number density of electrons in 1 meter cube, because the material is there 1 meter cube, and thus we have got the result.